Let's get started with lecture 26. So we've been discussing the interference of light. More generally, we've been talking about physical optics or wave optics. And the first model we talked about was the double slit interference. So let's just review a little bit. So we had two narrow slits which we can treat as point sources. They're very narrow. This is a view from the top. So the interference phenomenon, we can think of it as a two-dimensional thing. Imagine the slits just go all the way through, and then we put a screen at distance from these sources. So we call that distance L. The distance between the two slits was D. And then we were interested in the pattern of interference fringes that appears on that screen. So there's an exact solution, right? We can find the nodal lines, for example, which are some hyperbolic curves, and figure out where they hit the screen. It turns out it's a bit cumbersome, and in most scenarios, the screen is a long distance from the sources, so we can use approximations that simplify things quite a bit and allow us to much more easily think about the dependence of the locations of the fringes on various properties like dl and the wavelength of the light. So again, the approximation had two stages. So we had one approximation when L is the largest length scale. So L is really large. Therefore, if you take some point on this screen, this is going to be a tiny angle here between the two lines that connect the sources to that point. So basically, if you look closely in this region, these lines are almost parallel. This line and that line. If that angle is 0, they're parallel. I mean, that's an approximation, of course. If they cross, they're not parallel. But we can make the approximation that the angle between them is very small, so we treat them as parallel. And there's going to be some angle, like if you zoom out, you basically don't see the distance between the sources if they're very far from the screen. So there's going to be some angle, you can imagine maybe from the middle point if you want to be precise. But then if all of these lines are getting squished together, it doesn't matter. So let's say there's some angle theta here. So if you draw a line perpendicular to this, from this one to that one, this length seems to be a good approximation for delta r. So in this limit, we had delta r approximately equal to d sine theta, where theta is roughly the angle from the sources, from the slits, to the point on the screen you're considering. And we're in the limit of d, the distance between the slits, much smaller than L. So we don't really see that separation if you kind of zoom out. It's just some overall angle. All these angles are similar, right? The assumption is that all these lines are almost parallel, that the angles between them are really tiny, so they all roughly have the same angle. So making that approximation, we found that for constructive interference, we want delta r, which is d sine theta, to be 2m pi, an integer multiple of pi divided by, an integer multiple of lambda, which then makes a phase an integer multiple, makes a phase difference an integer multiple of 2 pi. So we want this to be m lambda. And for destructive interference, we want delta r, which is approximately d sine theta, to be m plus a half times lambda, right? Each half lambda gives a phase difference of pi, so that makes them out of phase, leads to destructive interference, and then another m lambda just shifts things by a multiple of 2 pi, shifts the phases by a multiple of 2 pi, which doesn't change the sines and cosines. All right, so those were our conditions. So that was the first level of approximation, and in this approximation, theta does not need to be very small. As long as d is much smaller than L, this works. And then if you want to find, let's say, the distance on the screen, so let's say this is the screen, these are the sources, we're taking the limit that d is very small, so theta may be a relatively large number. And then if you have, let's say, some distance ym here, either to a bright fringe, a point of constructive interference, or a dark fringe, a point of destructive interference, we can write ym as L tangent theta. And we can label these by theta m, right, in both cases. So for relatively large theta, the best way is to, if you want to find, for example, ym, to find theta, which becomes like the arc sine of m lambda over d, for example, and then find the tangent of it, right? So that's one level. We can further for a small, so if also the angles are small, we can make the small angle approximation. We have sine theta is approximately equal to tangent theta is approximately equal to theta itself, right? Thinking about a unit circle and a tiny angle here, right? So theta is that, which is the length of this curve here. Tangent theta is the length of this vertical line here over this thing here, which is slightly less than the radius. And sine is again that vertical line over the radius, which is 1. So we see that in the limit the theta becomes small, they're all roughly equal, and that also follows from just Taylor expanding the sine function and the tangent function around theta equals 0. Okay, so in this limit things even simplify further. So we can write d theta m is approximately m lambda, let's say constructive, and then ym is L theta m. So ym becomes m lambda L over d, right? Theta m is m lambda over d, so that's constructive, and then ym is m plus a half lambda L over d. That's for destructive. So in the limit of small angles, so if you have these fringes, let's say, again, the screen is here, the sources are there, you're not going too far. You're looking kind of close to the center. So there's going to be always a bright spot in the center. The distances are the same to the center, right? Just because of symmetry. And it also applies to the m equals 0 case of constructive interference. And so if you're not going too far away, you're in that central region, we can make use of this simpler approximation, and it gives us very clear idea about where the fringes are, how they depend on various length scales. So in particular, if you increase lambda, if you increase the wavelength, if you increase the distances between the fringes, if you increase d, you bring them closer, you decrease y. And if you increase L, again, you increase y. Another thing was if you pick like two consecutive fringes, let's say for m and m plus 1, then in this approximation, the distance delta y becomes independent of m. Right, so if you take either, both for constructive or destructive, that's just lambda L over D. So that's also a useful expression to have in mind. Okay, so let's continue this discussion. So now I want to talk about the intensity of light on the screen. So far, we identified the places where they're maximally bright, we get constructive interference, or they're dark, we just have destructive interference. But of course, there are other points on the screen, and every point, gets some superposition, right? So most of the points on the screen are somewhere in between. They're neither fully destructive nor fully constructive. There's something in between. And this gives rise to a pattern of intensity. So definitely like the points of destructive interference must have the smallest possible intensity. In the limit where we assume the amplitudes of the waves arriving there are the same, that's 0. And the places where we have, let's say, the bright fringes must have the maximum. So let's say this is kind of a central line, that's a bright fringe. And if you think about the intensity, well, it must be some kind of a maximum here. It goes to 0 at the next dark fringe, then goes back up to the same maximum in principle, the next bright fringe, etc. And of course, this is symmetric. So that's in this idealized approximation where we assume, that let's say you have one source here, one source here, you have some point there. You assume that the difference between the amplitudes of the waves arriving here and there can be neglected. We know that's not strictly correct, right? We know that the amplitude, if it's like a two-dimensional thing, if they're long, narrow slits, the amplitude should go down as 1 over square root of r. So if R1 and R2 are a little bit different, the amplitudes will be a little bit different, and then the dark fringes won't be completely dark, And then, of course, as you get farther, these distances, they fall together, you should get darker. So in longer distances, you kind of fade away, right? So this is ideal. And in a more realistic case, you're going to have a little bit of a decay as you move away from the center. Okay, so in the ideal case, let's try to derive the shape of that intensity of light. And we know that the intensity is proportional to the electric field squared, right? The electric field is what gets added. We find the superposition of the electric fields from the light from these two sources. So I don't know. So let's say we have E1 is A sine phi 1, right? There's some phase so we're thinking about 1 point, and there's some phase for the light reaching that point from source 1. There's some phase for the light reaching that point from source 2, and we're assuming the amplitude is the same, making this idealized approximation. So sine phi 2. Therefore, we're just writing it. So phi j, where j is 1 and 2, is k rj minus omega t plus some phi naught, right? Okay. So adding these, we had E1 plus E2. We derived this before, but let's write it again. We can write the sum of two sines as a product of a sine and a cosine. So this becomes 2a sine of the average phase times cosine of the phase difference over 2. Phase difference is just, let's say, phi 2 minus phi 1. And then we see in delta phi, the time dependence goes away. So all the time dependence is in this term. So you have like some kind of harmonic oscillator. The time dependence is there. And the amplitude, so let's say A becomes 2a cosine delta phi over 2. So if we consider sources that are in phase, that means phi 1 naught is equal to phi 2 naught, right? So if you shine, let's say you have two slits here and here, and you just shine one laser on both of them, there's not going to be any phase difference between the two, right? They both originate from the same laser. So this wavefront reaches these two slits at the same time, and then you would get a wavefront emanating from these two at the same time. So the sources will be in phase in this experimental scenario if there are two slits in front of the same light source. So then this one just becomes the phase difference we've been calculating, right? 2 pi over lambda delta r, where delta r is again the difference between the length traveled. All right, so now we know that the intensity is proportional to amplitude squared. So it's going to be proportional to cosine delta phi over 2, cosine squared delta phi over 2. So to figure out the coefficient, it's easier to just think about the maximum intensity. So let's say here at the center, clearly that cosine is 1, right? Delta phi is 0, cosine of 0 is 1, you get the maximum intensity. So let's say here your intensity is I naught, maximum intensity. So, and that's when that cosine squared is 1. So we know when cosine is 1, it must be I naught. So we can write I is I naught times cosine squared delta phi over 2, which is pi over lambda times delta r. All right. It also helps to relate this to the intensity of individual sources. So if you just had one source, let's say you block the other. So again, you have your two slits here and here, right? And let's say I block this. Then what is the maximum intensity that I get from just one of these? Well, it's going to be proportional to little a squared, right? There's no interference, so whatever the coefficient is, it's going to be proportional to a squared. This maximum, when cosine is 1, is proportional to 2a squared. So we can write I naught maximum from two slits is the same as 4I1 maximum from one slit. So we can write I in terms of the intensity that only one source would produce. So that's going to be 4I1, and it's going to be cosine squared pi over lambda delta R. Our delta R we can also relate to the distance on the screen, right? So basically, if I use let's just rederive this. So let me just keep this delta R. So we said delta R is roughly d theta, right? And the distance on the screen, y, is roughly L times theta. So let's say delta R becomes d, and theta is y over L. So we can plug it into our expression, and we find I is 4I1, the intensity from one light source, cosine squared pi dy over L lambda. So in this approximation, basically, let me write this like, just switch the order of y and d so you don't confuse it with some differential. So let me write it as y times d. Okay. Yeah, these are just all are length, and they multiply one another. So at some arbitrary distance from the center, y, we can know the intensity of light, and this is the shape of that curve that we kind of predicted. It's a cosine squared kind of curve. All right. So what we derived is just this expression here, right? So we have two slits, and of course the places again where that cosine squared is 1, we have the bright fringes, and places where cosine squared is 0, we have the dark fringes. Okay. And this is, of course, the more realistic case because the intensity is not uniform, right? The intensity depends on R, right? As you move away, you travel longer distances, so your amplitudes for the individual waves from the two sources that are interfering, that kind of decreases. It decays with distance, and there should be some overall envelope for this decay. Okay, so here's a quick question. Try to read it, pause the video, and find the correct answer. All right, so that's the double slit interference pattern on a screen. And if we double the amplitude of the light wave, what happens to the intensity of the central maximum? Well, we know that all intensities are proportional to amplitude squared, electric field squared. So you double A, then all intensities get a factor of 4 because they're proportional to the field squared. Okay? Now, so the next topic I want to talk about is something called the diffraction grating. So the idea is that instead of having just two slits, you have n closely spaced slits. So kind of the motivation for this is that it it gives very narrow bright fringes, so it just makes experimentation much easier. The bright fringes will be very localized and well separated. So let's try to think a little bit about this. Again, the equations are actually the same for bright fringes, are the same as the double slit, but the shape looks different. When you have a bright fringe, you don't have much bright regions near it. So it just makes things much sharper. Okay, to understand why this is correct, we don't really need to do any calculation. So everything we did for the double slit works here as well. So let's just look at a figure. So again, we make this approximation that the screen is really far away. So all these lines from all the slits to a point on the screen, they can be treated as parallel approximately. And then, well, if you take like two of the two parallel lines, so let's say the slits are placed distances d apart, right? So the double slit will just have two of these a distance d, and we figured out that the phase difference between these two is d sine theta, right? And to get a bright fringe, we just we require that d sine theta is an integer multiple of the wavelength, so they're in phase and therefore interfering constructively. Now, if that condition is satisfied, then, well, all the neighboring ones have a phase difference of m lambda, and then, so they're in phase. And if you take two arbitrary ones, so let's say I take this and this. So let's say d sine theta is m lambda. That gives a phase difference of m2 pi between these. So then between this and this, it's like d is doubled. So again, the distance is multiplied by some integer. So I get 2m times 2 pi phase difference. Again, it's an integer multiple of 2 pi. So all of these, any pair you take, they're going to be in phase, right? They're the difference in the length traveled is m lambda, which is d times sine theta, times, something, some integer. So let's say you take this and this, the distance is 1, 2, 3, 4 d's. So you multiply that by a factor of 4, but again, any integer multiple of lambda gives you no phase difference. They're all in phase. So the same condition that worked for the double slit implies that the points of constructive interference for the double slit will be constructive here as well. It turns out that, these tend to be a bit wider, so kind of this secondary approximation that we made where we treated theta as small, in practice doesn't work quite that well for the diffraction grating. So we're going to stick with just first level approximation where we say, yeah, d sine theta is m lambda, and then y, the distance on the screen, is L times tangent of theta. So that's just what I said, right? So if you have this condition, you're guaranteed to get a bright spot. With more thought, one can show that you cannot get fully constructive interference between all of them if this condition is not satisfied, but we don't need to go into that much detail here. So yeah, so that's basically these equations worked the same way for the double slit as well. So here, for example, the first bright fringe appears where, delta r is just lambda, delta r between two neighboring ones, so m equal 1 in this equation. The next one is m equal 2, etc. Now, as I said, if you think about the intensity, then the intensity gets kind of more squished, right? So previously we just had this cosine squared curve, which was more uniform ups and downs. Now it gets, when you have a peak, when you have one of those maxima, as you move away, the intensity goes down very quickly. So the image that you get, or the fringes that you see, become much sharper. And also, so how does the maximum depend on the intensity of just one of these sources? Well, when we had two slits, we said the maximum you have constructive interference of just two of them, so the amplitude is twice the amplitude of the individual ones. Intensity goes like amplitude squared, so it becomes 4, let's say I1 at the maximum. So here, if you have n of these, then your maximum amplitude, let's say here, is n times the amplitudes of the individual ones, and your I max, the maximum intensity, is n squared, right? So it also makes the intensities quite large and makes those maxima very bright. Okay. And so, as I said, because these fringes become really sharp, so experimentally it becomes very easy to detect where they are. They're not blurry kind of lines and you don't know, okay, where is the center, where is it brightest? Really, you have a very bright, very sharp, narrow line. We talked about it before, that you can use this to measure the wavelength or the frequency of light. You can even do that with the double slit, right? You know the dependence of the position of the fringes on the wavelength, so you can see where the fringes appear, measure the length from, let's say, the central one to one of those fringes, and from that extract the wavelength. So using a diffraction grating makes it much easier, and that's really the standard way. You're not going to try to measure the wavelength using the double slit, because it has quite a bit of error, right? How do you identify? Whereas here you just see these sharp lines, and you can measure their position quite accurately, and then from that trace back and find the wavelength of your light. All right, so here's a quick question. Pause the video, read it, and try to find the answer. Okay, so I hope you managed to find the correct answer. So we have a lab experiment. We have a diffraction grating that produces an interference pattern on the screen. And if the number of slits is increased with everything else, including the slit spacing, the same, then what happens? What happens to the fringes? Well, we just found, right, the expression for the positions of the fringes. The condition was that d sine theta is an integer multiple of lambda, the wavelength. So it doesn't depend on n, on the number of slits. So the fringes should stay where they are. So A is wrong, B is wrong, E is wrong. So we're in between C and D, right? The fringes must stay in the same place. And as you increase, we didn't really prove this, but it's something we saw, like that's the advantage of the diffraction grating. When you go from 2 to some larger n, what happens is that you get these brighter and narrower fringes, much sharper and brighter, right? The intensity, I mean, you can see that goes like n squared. So the brightness at the middle of the fringe is clear that it has to go up substantially. And another thing that we haven't discussed in detail is that, you have this narrowing of the fringes. So in the same way that we found let's say the intensity as a function of y, for the double slit, and it had this cosine squared. I mean, one can find the intensity as a function of y. For a more complicated case with, let's say, 100 slits, and the pattern that emerges is that as they become more bright, they also get narrower and much sharper. All right, so yeah, C is the correct answer. All right, so we talked about the double slit interference. We talked about the diffraction grating, which is like many slit interference. And the assumption was that we have these really, really narrow slits or openings where we can basically treat them as point sources for light. But if the opening has some width and has some shape, I mean, there are different places, right, along this opening. So even if you have just one slit, but it's not extremely narrow, so you can treat it as just one point, there are different points, right? So this is just one slit, right? And there's a point here, so light goes here and gets diffracted from here, from various points on this. You have, on various points inside the opening, you have sources of light, if you wish. So it's kind of like a continuous limit of a diffraction grating. So it's conceivable that even a single slit should produce some interference fringes. Okay, so first let's try to play with a simulation with just a single slit to see if we can see anything. So yeah, this is green light, some separation between slits. Let me put a screen here and let's plot the intensity there. All right, so we turn on our laser. It's going through one slit, so in this limit it seems, yeah, we just see some kind of a broad central peak. So it's, yeah, we don't see any fringes, right? It seems in this limit for a very narrow slit, as expected, well, there's very low intensity and it just monotonically decreases from a bright kind of central region. But let's say we increase the width. So something interesting happens, right? We already see some signs of a non-monotonic behavior, right? We have this bright central peak here, but it seems this comes down and goes up a little bit. So let's increase that even more. Let's see if anything changes. Yeah, so we clearly see this type of non-monotonic behavior, right? We have this central peak, it comes down, seems it goes up and then goes down again. So roughly some secondary fringes seem to be appearing. So we experimented with the width of the slits. Let's move the barriers, so we change L, the distance between the screen and the slit. Again, it seems that, yeah, I mean, these things got shifted away from the central. You can also play with the frequency, so I maybe increase the frequency. Yeah, here we can also almost see it in intensity, right? So it's darker here and kind of brighter in this region. So it seems that making the slit wider, increasing the distance, making the slit wider, yeah, increasing the distance and increasing the frequency can help us see fringes better. All right, so this is a picture of what we would see in an experiment with a single slit. So you have incident light of some wavelength, and you put a screen a large distance from this, so L is much larger than A. Let's say the width of the slit is A. And yeah, as usual, we're going to get a central maximum, and then there are these secondary fringes, secondary maxima. And the intensity kind of decays as you move away from the center. So we want to understand this pattern better and try to figure out, again, the locations of the fringes in some approximation. All right, so we make use of the same approximation that we used before for the double slit and the diffraction grating. So basically the idea is that if the screen is really far, if you connect various points along the opening, right, to one point on the screen, these lines, they have very tiny angles between them, so we can treat them roughly as parallel in the limit of very large L. So clearly, like if you go to the center, right, the angle is 0. All the lights are just going straight ahead. So that gives us constructive interference, right? There is no phase difference between any of these. They're all in phase. So everything adds up constructively. So we know that right in the center we have a maximum in the same way that we had one for, let's say, the double slit. Now let's say we consider a point that's some distance from the center, right, on the screen. So of course there's some subtle issue here, right? We don't have these well-defined point-like sources like in the diffraction grating. It's really a continuum, right? So you just have light going through all the points inside this slit. But let's just, for the sake of the argument, we break it up into n pieces and imagine there is like one source in the middle of each of those n pieces, and ultimately we want to take the limit of n going to infinity, right? But it makes it much easier to think about this discrete case, so we can use some of the technology that we developed before and apply, for example, to the grating. So yeah, so then we have a whole bunch of waves from various points along this opening that has a width A. And let's say we want to identify, for example, the next place where we get constructive interference. So we know theta equals 0 obviously has constructive interference. So what we want is we want all of these guys to be in phase. So how can we do that? Well, so let's consider just a couple of them. So for example, let's take let's consider 1 and 2. So we have 1, 2, 3, 4, 5, 6. These lines are numbered in some way. So if I take 1 and 2, so 2 is right in the middle, 1 is at the top, okay? And the distance between them is A over 2, is half the width of the slit. Now, so you see, we can kind of pair up, right? Let's say I pair up 1 and 2, 3 and 4, 5 and 6, and all of these have a separation of A over 2. Now, if each pair interferes destructively, right, then 1 kills 2, 3 kills 4, 5 kills 6, and we're going to get a dark spot, right? So for the case of destructive interference, we want to get, let's say, 0 intensity. We want everything to add up to 0. And if they cancel out in pairs, then that happens. Then it's going to be a dark spot. So we can see if the phase difference between one at the top and one at the center, right, is pi, for example, then the whole intensity will be 0. Okay, so we have this way of identifying the positions of the dark fringes using this kind of trick, breaking up all these waves, right, into pairs, distance a over 2 apart from each other. So let's think about the positions of the dark. So let's say single dark fringes. We have our opening here with A. This is the center. And we measure, let's say, some distance y from the center. So again, let's zoom in, right? So if I zoom in, all of these move at some angle theta. And if I have, let's say this is a over 2 from the center to the top, and then you move the same distance below, so you pair up this with this, you keep pairing up all of these wavelets, all of these waves from different parts of the opening. So if I have a over 2 sine theta to be m plus a half times lambda, then all pairs interfere destructively. And that gives me a dark fringe. So if you make the small angle approximation here, we find, let's say we multiply that equation by 2 and we set sine theta equal to theta. In the small angle approximation, we have theta, let's call it theta m, is approximately 2m plus 1 times lambda over a. So we found some angles, right, where we are guaranteed to get destructive interference. In this case, it's an odd multiple of lambda over a. But we haven't shown that these are the only angles, and it turns out that they're not. So these are only half of the angles, as we'll see later. So it turns out dark fringes appear at theta p to be equal to p times lambda over a, and p is 1, 2, 3, 4, etc. So it can also be an even number. So the way we can kind of convince ourselves that this happens is, instead of considering waves from sources a distance a over 2 apart, let's consider waves a distance a over 4 apart. So again, this is our opening here. That's the center. Okay. So this is a over 4. This is a over 4, a over 4, a over 4. And we have these waves from all these points moving at some angle theta. Okay, so it's a different type of pairing up the waves. So let's say I have this and this giving me destructive interference. So let's say I say a over 4 times theta, let's call it theta n. Let's say that's n plus a half times lambda. Right, so if that happens, you know, this cancels with this, somewhere in the middle you come down a distance here, cancels with this. And similarly, so basically in this region we get pairwise cancellation, but the same thing applies here. So this now cancels with that, a little bit below, cancels with this. So we come up with this different pairing, and all the pairs again interfere destructively. So that gives me theta n is four n plus 2 times lambda over a. Again, some integer multiple, so now some even integer multiple. But now it's an even times an odd, right? So it's, let's say 2n plus 1 times lambda over a. So we found more of these p's. So previously we had all the odd ones. We had 1, 3, 5, etc. Now we found 2. We didn't find 4. We found 6. So 4 is 2 times 2. So you divide it by 2, you get an even number. But we found 6, etc. But we can keep going with this argument. So in particular, consider any p. So let's say theta p is some integer p times lambda over a. So any integer, right? You can write it as an odd number times a power of 2, right? So you can keep dividing it by 2 until you reach an odd number. So any p can be written as, let's say, I don't know, 2 to the q times 2n plus 1. And if it's just, let's say, my q looks like 9. Let me write capital Q here. Right. So some power of 2 times an odd number. And if p is like some power of q, then n is 0. Again, that works, right? That odd number is 1. Okay. So now suppose, you know, we divide this into a over 2 to the q, right? So we have 2 to the q of these pieces, but then each of them kind of cancels out with the next, again, using the same argument. So let's say I write a times 2 to the q right? In the same way that we had 4a over 4, we have 2 to the qa over 2 to the q intervals, and then each of them cancels out, like they pair up and cancel out, so that times theta of, let's say, q and n becomes n plus a half times lambda. Okay, so what do we learn from this? We find that theta of q and n is, let me write this again, it's some arbitrary number, right? Some arbitrary power of 2, so let me divide by 2 to the q plus 1. I just use my notation like this. So in this case where I divide, I get these intervals of length a over 4, 2 to the q plus 1 is 4, so q is 1, for example. And in the previous case, in this case where we just had a over 2 and a over 2, q is 0. Okay, so now this gives me, I divide by a, so I have this factor of lambda over a here. One of these 2's multiplies n plus a half, so it gives me 2n plus 1. And then I get 2 to the q here. So we see for any integer p, which can be written as some odd number times a power of 2, so this is p, right? I can come with some construction, some way of pairing up these different waves so they completely cancel out in pairs, and we end up with a dark spot. So this is a general condition. Again, let me write this again here, or let's highlight this. In the limit of small theta for finding dark fringes in the case of single-slit diffraction. So this is a good place to stop. We'll continue this discussion in the next lecture.